Good afternoon. I am Tatiana Perrotin. I'm in the last few months of my PhD in the plasma propulsion group, and I'm gonna talk about my thesis studying low-power cylindrical Hall thrusters. So first of all, the motivation for my thesis, the main motivation is the need for low-power electric propulsion. Let's say in a short, the best candidate for this is Hall thrusters because it's one of the most mature electric propulsion technologies. It's been developed for decades. It's one of the highest performance ones as well, and it's a solution that offers high thrust compared to other electric propulsion devices. For those who are not familiar with the Hall thruster, you have a schematic there. Basically, it has an annular discharge chamber. You have a radial magnetic field and an axial electric field between an anode at the back and the cathode that is outside. And you have electrons that are ejected by or produced by the cathode and that travel towards the anode and get trapped in an azimuthal drift. That's where they start ionizing the neutral gas that comes from the anode. And those ions that are created are accelerated actually with the electric field. And some of the electrons from the cathode neutralize this ion beam. So the challenges in downscaling Hall thrusters are, first of all, that there are no scaling laws. We don't know how to scale them to a specific target power. The miniaturization has some difficulties. It causes thermal issues. It causes problems of saturation of the magnetic circuit. It gets difficult to manufacture or to keep integrity of the pieces. And you can see the top two pictures. It's a comparison of one of the biggest Hall thruster that exists and one of the smallest ones. You can imagine the difference of scales. The problems that you encounter are not the same. And then decreasing the size of the Hall thruster, you get problems with increasing wall losses, erosion, and that affects the efficiency and the lifetime. Since you always need a neutralizer for Hall thrusters, you have also problems of cathode of neutralizer. When you size them for low current, you have issues. They get unreliable. They get less efficient as well. So our idea was to develop a cylindrical Hall thruster to address at least some of these issues. Why is it a good candidate for this? It operates the same way a normal Hall thruster does, at least the general principle. But in this one, you see there is no internal pole, so it's a fully cylindrical or almost fully cylindrical channel. So you remove one surface to erode, you gain volume compared to the surface where you lose power. You avoid some small components, and in general, the engineering is a bit easier. And this is a promising device that is not conventional, and it's still recent. There are few prototypes, so there is a lot of research to do on it. And there is need for experimental data to understand the specific physics of this thruster and of Hall thrusters in general, and how to optimize their design. And as well, we need experimental data to validate models, but my colleagues will talk about it better later. So the approach was to design and build the thruster. You can see some of the steps of the design of the first prototype. Then there was a small part dedicated to modeling the plasma discharge with the code of the EP2 group. And then the core of the thesis was the characterization, extensive characterization of the thruster to understand how it responds to different inputs, to measure the plasma properties, to understand the physics inside, and how the performance is affected by those properties. And then the step after that, of course, is to iterate on the design, the testing, and the modeling as well with experimental input to better match the numerical results. Well, the opposite. So there is already a second prototype that was designed and built and that is ready to be studied. So for the first part, at the beginning of the thesis, after the design of the thruster, I dedicated some time to doing preliminary studies with the hyphen code. There is a hybrid plasma code. And it was mostly to understand the behavior of the plasma inside the thruster by varying some parameters, mostly geometric parameters, so the anode location, injector location, the dimensions of the channel, some wall properties, and the position of the cathode. And from that, I got some insight on where it would be what dimensions would be best. I got during the thesis a small side quest, developing diagnostics for electropropulsion that I didn't directly get to use on my own thruster, but that I used on another thruster of the group, and that was that was also in collaboration with ETPAC, the team working on ETPAC. And it was compared with theoretical models for tethers. And the main conclusions I got from that, even if we had some useful results, is that we definitely need to develop better theory and better modeling for probes, for diagnostics adapted to electropropulsion plasmas. And then the most important part of my work was the characterization of the prototype that came in 3 major campaigns. The first one was dedicated to the measurement of the plasma properties in the far field of the thruster with essentially 3 electrostatic probes. And from that, I varied different parameters, mostly input parameters, so the magnetic field, the mass flow rate, and the discharge voltage, and observed some trends of behavior in response to those parameters. The next campaign was dedicated instead to measuring properties of the plasma inside of the discharge chamber, which is much less accessible, and that was done with optical diagnostics to not disturb the discharge. So in this case, it's Doppler velocimetry done with laser-induced fluorescence spectroscopy. And the main, coupled with modeling of the spectra to retrieve the ion and neutral VDF, regardless of the conditions of magnetic field or of presence of isotopes, for instance, of xenon. And with this, we saw mostly that the acceleration in that thruster takes place mostly inside of the channel, which is very different from typical Hall thrusters, and that we have a lot of recombination of ions at the wall, at the lateral wall, and we also acquired some useful data, for instance, for modeling. And the last campaign was dedicated to measuring the performance of the thruster. So that was done with direct thrust measurements with the thrust balance that we have here in the lab of EP2. And again, electrostatic probes measuring properties of the ion beam in the far field to decompose the performance from the thrust measurement. So from the thrust balance, we measured a matrix of mass flow rates and discharge voltages to understand how the thruster behaves, how efficient it is at different points over the whole operating envelope that we could cover. And we saw that the efficiency depends strongly on the discharge voltage in that range, and that it saturates for all the mass flow rates, it saturates at a certain discharge power. In parallel, as I said, I measured the ion current density with a Faraday cup, which showed asymmetries in the plume, important divergence, which is also quite specific to this type of thruster, and in this case, more specific to this very device, that it needs a large discharge current to produce ion beam, so it's not using the current very efficiently. and that, as other people have seen in CHTs, that we have most likely a significant number of multiply charged ions. And then I measured the ion energy with a retarding potential analyzer, and the main finding was that it appears we have 3 ion groups of different type of energy that are dominant in different locations of the plume, and that appear to come from different ionization region or production mechanisms. Then I combined the data from those probes to estimate partial efficiencies, and
it's okay.
yes. And this confirmed that the main drivers of efficiency losses in this device are the divergence and the current conversion, so of discharge current into ion current. And the first way to tackle this is going to be to optimize the magnetic field. Last finding of this campaign, very quickly, is that we observed a sort of correlation between the regimes of discharge current, higher or lower, associated with the presence of high-frequency oscillations, which appear to affect the performance of the thruster. And this is something that is going to be studied more in depth in the future. And so now I'm left with writing the thesis. And I have plans for future research involving the 2 thrusters that I designed and hollow cassettes, development of hollow cassettes. Those are my achievements for the whole PhD. And if you have any questions, I'll be happy to answer.